So let's start the first quantum algorithm, right? The Deutsche problem. So last time we started the Deutsche problem, the first of our Deutsche algorithm. The first thing we need to understand is what this question is about. So we might have a function. We don't know what it is about. We don't know what is inside this function. This function may be very difficult to compute. It can take a lot of time. But this function turned out to look simple from the input and output perspective. The input is only 0 or 1, okay? And the output is also 0 or 1. Although the input is so simple, output is so simple, but it can be very difficult to compute, right? You can imagine that can need a 1 billion transistor to compute a certain Boolean function. Okay, is that okay? Yeah, I hope you agree that we can have such a question, right? This question may be as complicated as I see a cloud in the west of the sky. Is it going to rain tomorrow? 0 is no cloud there. 1 is there is a cloud. And then the output 0 means it's not going to rain tomorrow. The output 1 means it's going to rain. And you know this is very complicated, right? It involves a lot of computation. So for this type of function, Deutsch problem is a reduced problem, a subset of so-called Deutsch-Jozsa problem, which is involve many qubits. You can take a look in my book, right? And then or Google to understand it. We only look at the simplest one, only 1 bit input. If I can only have 0 and 1 as the input and 0 and 1 as the output, there are only 4 types of function that's possible. The first type is when input is 0, output is 0. When input is 1, output is 0, right? So they have the same output no matter what you put in. So this is called a constant function, okay? Or you can say this is a long balance function. Or you can have the input is 0, output is 0, input is 1, output is 1. The number of 1 and 0 output are the same, and we call it balance. Just a name, okay? You can say it is long constant, right? And or the input is 0, output is 1, input is 1 or output is 0, then this is a balance function also. And the last one is when input is 0, output is 1, input is 1, output is 0, then this is a constant function. No matter what input is, the output is 1. Okay? So our question is, if I give you a function f, can you tell me whether this is a balance function or a long balance function? Okay? What do you need to do if it's a classical computing? I give you a function. You want to check whether it's a balance or long balance, right? Or whether it's constant. What do you need to do? Yeah? Not even statistically, just put in all the possible input and check the all possible output. Then you know whether it is constant or balanced, right? That is what you need to do. This only have 2 possible inputs, so I put in 0, find what's f of 0, and then find what is f of 1. Based on the output, I can tell you whether it is constant or balanced, right? Just like here. Okay? But if I use quantum computing, I can do this in one computation. Now, if you use a more sophisticated Deutsch-Jozsa problem, which is not here, right? You can have many qubits, you still just need to do one computation. So this is so-called super exponential. I mean, it's just a constant. No matter how many qubits, you just do one computation. Okay, we'll talk about this complexity more. But now, do you understand the problem that we are trying to solve? I give you a function, you don't know what is inside. You need to decide whether it is constant or balanced. Okay. So last time we did an overview. We do it again this time. The first thing is that if you want to do this in quantum computing, you must encode the information of the function, right? You must have something to tell you what this function is about in order to do the calculation. So we do this by using a quantum oracle. We will detail this more later today, what is an oracle, but now you just take it for granted. It is just a gate. And this gate, it has this property. It's going to take two inputs, means in this case, two qubits, x and y. And its output is going to be x and y exclusive f of x. What does it mean to this y exclusive f of x? It means if, for example, if it turns out x equal to 1, y equals to 0, then what is y exclusive f of x? And if, let's say, f of x equal to 1, what is y exclusive f of x? Y is what? 0. F of x is 1. So 1 exclusive 0 is 1. Okay? Does not make too much sense to you now. This is just an overview. I only need you to understand we do need to create a quantum oracle, which is just a gate. Remember what is the meaning of a quantum gate? It defines how you transform the basis state. How many qubits do we have here? 2 qubits, right? So how many basis states do we have here? 4, because it's 2 to the power 2, right? So this quantum oracle I represent as this symbol. It's just like other gate, exclusive or gate, control not gate. It tells you how you transform xy. Xy can be 0, 0, 0, 1, 1, 0, 1, 1. And it gives this output. How do you calculate? X is not changed, but the second qubit, the least significant qubit, become y exclusive f of x. So this gate encodes or contains the information of the function I'm interested in, okay, in order to do this algorithm. Okay, that is the first step. You do need this. How do you get this? We discuss later. Is that okay? After this, like every one of you and some of you said last time, if I want to achieve this speed up to do the computation all at one time, we have been spent so much time on quantum computing. Naturally, you will think I need to do superposition. I need to create a superposition state. And I chose to be plus minus. Not me, Deutsche. They chose that because they're smart. They came up with this algorithm. Some of you came up also, but last time you proposed plus plus. But you will find that plus plus won't work. Okay, but if you keep doing that, eventually we'll figure out plus minus will work. So this is nothing special. You will appreciate. You will just see very normal now, natural now, right? Very natural now. If you want to do a quantum parallelism, you must create a superposition state. But what type of superposition state really depends on the nature of the algorithm. In this particular case, we choose plus minus. Then you create the superposition of 0, 0, 0, 1, 1, 0, 1, 1 with some plus and some minus coefficients. Is that okay? Yeah, so we have superposition. After that, what do you do? Yeah, do the computation. But in quantum algorithm, we usually use the quantum oracle to do the computation, right? It will be clearer later why we have this structure of oracle. But here, let's just appreciate what it is going to do. Don't worry about the math yet. This is just an overview. Just remember that I apply this oracle to this single state. Again, this is how many qubits? 2 qubits. Very good, yeah? Which is a superposition of 4 basis states, right? Remember this. So this is just one single state. I apply the quantum oracle, which is just a quantum gate after all, or just a quantum circuit. Because of this, we can do distribution, right? Based on this distribution rule, because this is Hilbert space. We learn about that. And yeah, If you want to be fancy, yeah, because the Hilbert space obey the distribution rule, right? But we said that even you don't know Hilbert space, you treat this very normally, because any first grader or maybe third grader came into this classroom, see this, he or she won't be surprised. Say, oh, this looks like the distribution rule I learned in my school, except he or she doesn't understand why you put 0, 0. Why are you so stupid? Put 0, 0. This is just 0, right? Other than that, everything is very normal. We do this and apply this to individual bases. We are going to the details later, but do you see that? It's just based on the definition of this quantum oracle. This quantum oracle tells us how it's going to operate. So if I have, let's say, 1, 1, I keep 1 here, and then 1 exclusive f of 1, right? Because this is x. This is just like x, x exclusive f of, not x, it should be y. Y exclusive f of x. That is exactly what I'm writing here. Go back to here. X, y exclusive f of x. X is 1, y is 1, f of x is 1. Okay? So after this, then I'm going to do a measurement. Now let's look at this. If I try to measure in the plus minus spaces, I look at this one. This is just from here. Now, if this is a constant function, okay, or long balance function, is constant, means what's the relationship between f0 and f1 if it is a constant function? Same. Very good. That's why f0 is f0. f1, I just write it as f0. f1, write it as f0 because they are the same. I can write this because if it is constant. Okay? And then go through factorization. You see, eventually it becomes an unentangled state with the most significant bit in the plus state and the least significant bit in this state. Now, if I do a measurement and I find that the most significant bit is plus, then I know that this must be a constant function. I did not show you here. If I get minus, then this is a balanced function. Don't think too hard. I have not gone through the math yet. I just try to let you know what is the Deutsche algorithm and how they came up with this, right? Let's quickly review one more time. Encode the function you want in a quantum oracle. You definitely need to encode the information about the function. Otherwise, how can you understand whether this function is constant or balanced, right? Long balance or balance, correct? Superposition, very simple. Because I'm doing quantum parallelism, that is the power of quantum computing. I need to come up with some superposition state. Operate on the quantum superposition state, then I can do the calculation in one shot parallelly. And we know in the first class already, you get so many information. No use to me, I cannot access them, right? What can I do? I do some special measurement. Based on the property, I've proved that if it is a constant function, I always measure plus in the most significant bit. If it is a long balance function, I always measure minus in the most significant bit. So if I measure it, I get plus, I know this is a constant function. If I get minus, I know this is a balanced function. And I only do this with one computation. Here is the computation, take very long time. Yeah. I will discuss the quantum oracle later. You need to have, there are two types of quantum oracle. This is exclusive or quantum oracle, another is phase quantum oracle. I will show you why we need that later. Now you just take it for granted. This is the given quantum oracle. Okay, so try to understand the overall picture first. Good question. Okay. So let's start the math, right? I believe only if you can do it yourself will you really understand what's going on. So we say that the first thing is we need to implement the quantum gate, which is the quantum oracle. And we are not going to understand its property yet, right? But we want to understand how to calculate. This is a unitary gate. You can call it is a quantum oracle. What does it do? As it's a gate, it must tell us that how it transforms the basis, right? When I write this as tensor product, I just try to remind you that it is a tensor product. Otherwise, I just put xy. This is the any input, right? But the most important thing, it tells us how it transforms the basis. This becomes x, y exclusive f of x. X obviously will be the input, y is related to our output. Okay, this is the relationship. Now, I know you feel confusing, but if I tell you this is just a gate, are you okay with this? Just a gate. I tell you I invented this gate will be useful for you to do this Deutsch algorithm. Do you agree this is just a quantum gate? Let's check. For example, if xy equals to 0, 0, I apply this to xy, what do I get? Anyone? I mean, I apply 0, 0, right? Xy equals 0, 0. So 0, 0, what do you get? No, I want you to do substitution, not the final result. Yeah, it depends on the function. You are right. What is that? 0. Exactly. So here I have a typo. It should not be cross. It should be a plus exclusive or. What is 0 exclusive or function? Exclusive something. 0 exclusive something. What do you get? I mean, does it change it? No, right? Because 0 exclusive 1 is 1. 0 exclusive is 0 is 0. So this is just equals to 0 f of 0. Very good. Okay. Now, what if I do this? 0, 1. What do you get? Just do substitution, right? Make yourself as a simulator. Follow the step by step. What is UF01? What do we get? 0. It means x is 0, right? And what is y? Just substitution. Tell me, what is x and what is y here? Yes, and then what would be the output? Just put in 1 exclusive f of 0. It's not difficult. You just need to keep track. That's why I spent so much time. I want you to be able to track all the qubit and know what you're doing, right? What is this? When one exclusive something, inversion, it becomes the negation, right? So it becomes bar f of 0. Right? I take the bar means that the invert, right? So if f0 is 1, it becomes 0. If f0 is 0, it becomes 1. I still don't know what is f0, and in this whole problem, I don't need to calculate f0. I just want to know whether it's balanced or equal, right? So the nature is fair, the God is fair. You actually can do you can find it with one computation, but you only know whether it's balanced or non-balanced. You don't know the value of each of them. You don't really gain something, actually. But if you need to know individual value, you cannot use quantum computing for this purpose. Okay? So we understand this, then we're going to use this later. And then we say we are going to prepare a state. Okay, and we just want to practice a little bit. What is plus? 0 plus 1, right? Tensor product. What is minus? 0 minus 1. And then what we need to do is just to go through the multiplication, right? And that's naturally we get the 0 times 0, negative 0 times 1, right? Plus 1 times 0, minus 1, 1. That is the states that I showed you earlier, right? But this time we do it ourselves using our hand, right? But particularly, yeah, just want you to realize this is plus, this is minus. Okay, then we continue the math. Now I apply, right? I'm not doing anything new, but now we go through the math so you believe what I'm saying, right? UF to the function I just created. I still remember what it is. I'm not looking at my cheat sheet, right? Because I know very well this is 1/2. I know this is a superposition state, and I remember this is plus minus, right? So I remember this. You need to have a feeling on the number, right? Is this okay? So because of distribution rule, I take out the F. I can get UF applied to 0, 0 plus, not plus, minus UF applied to 0, 1 plus UF applied to 1, 0 minus UF applied to 1, 1. Right? Just distribution. Is this okay? Any questions? And then what? This would be a good if you can memorize this, right? What does it do? UF applied to XY, give me what? Do you remember what we just said? X, Y, exclusive. F what? Fy or Fx? Fx. If you forget anything, you should choose Fx because it contains the function f of x, right? It cannot be f of y, right? That's a way. I mean, the point is, if you want to invent a new algorithm in the future, that is the line you want to think about, right? You cannot let me try to come up with oracle with f of y. Basically, it's meaningless because I want to know what is f of x. That is the function I want to calculate, right? So with this, let me do this. 0, 0 becomes 0, 0 plus f of, exclusive f of 0. And then 0, 1 is what? Okay, you are very fast. I don't do negation yet. I still do 1 exclusive f of 0. Make sense? And then what is this one? 1. Think carefully. It should be y, right? 1, 0. 0 is y. Exclusive f of 1. And then 1, 1, exclusive f of 1. And you should appreciate this, although it is very lengthy, but you really should appreciate, wow, yeah, I can computing f of 0 and f1 in one shot. Right? I don't know what's f0 and f1, actually. But they contribute to the final wave, final state. And I need to be smart to do something to extract the information I want. I don't care if it is going to be what is the value of S0 and F1. I care about whether they are balanced or they are not balanced. That's it, right? Okay, so let me simplify this one, like what you try to do now. This becomes 0, f of 0. Now, I hope you understand what is the main meaning of f0 in the cat, right? Cat is a state, a vector. This is just say you calculate it, then you describe what the state it is. Right? You tell me whether this is 0 or 1. Okay? This is 0. What is this? Negation, right? Like what you try to say. This one, it is still F1. And then this one, it is F of 1 bar. Now from here, you actually, maybe you come up with some idea already. Look at this. Hey, if they are constant, wow. If F1, if these are the same, right, they will get cancelled, right? And if they're not constant, maybe the other term will get cancelled. But you will find that you cannot do it here. However, that is the idea. And then you go further. Maybe I can transform in another basis so they will get cancelled. Right? And that is why you need minus and plus. And then now you bingo. Hey, that's why at that time I should use plus minus. Last time you proposed plus plus. I said it won't work, you try it. If you keep trying, you find it's all plus. Then you cannot come up with an algorithm of method that I can get a certain value when it is constant. Or I will get another value when it is balanced. And very naturally, you say, I need some minus. Well, let me try minus, minus. Of course, maybe it still doesn't work. Then you try minus plus, and turn out it works. And then you are Deutsche. Right? That is how I think. Of course, those are people, I don't know how they think, right? They come up with even a higher level, a more sophisticated theory. They can see those theory. They can deduce that easier. But this is also okay, right? Now, then what I'm going to do is say, I already told you the answer. We need to measure in the plus minus basis. But from here, we cannot see it, right? What we are going to do is, like I told you last time, to measure in the plus minus basis is the same as applying Hadamard gates and then measure in the 0-1 basis. We don't want to measure in the plus minus basis. So what I'm showing here is incomplete here just to show you that the idea. If you can measure in plus minus basis, we are basically done. You see that I derive here, but ignore this one, right? We're going to still want to measure in the 0- basis. So I will apply the Hadamard gate, and then I can do it in the 0-1 basis, right? So this is another step. I'm going to apply the Hadamard gate to the first qubit. So what should I do for the whole system? I only want to apply Hadamard gate to the first qubit. So what is the overall gates I need to apply to this system? Yes, right? That's what you did in the midterm, right? I only want to apply the Hadamard gate to the first qubit, right? I cannot just apply the first qubit, right, for the whole matrix. So that's why I add this one, okay? So let's do that, right? So apply Hadamard gate, then it means that I'm going to apply the whole thing to here. Then it becomes what? First, I will keep this half here. When I apply the Hadamard gate to this term, what do you get? I apply this gate to this term. What do you get when you apply Hadamard gate to 0? One over square root 2, 0 plus 1. But what happened to F0? It doesn't change. You get the identity. Okay? Make sense? I continue the same thing for the second term. What do you get when I apply the Hadamard gate to it? Still, because it's 0, I get this one, right? And the second term doesn't change. I only apply to the first qubit. Continue on the third one. What do I get? 1 apply to 1, right? So I get 0 minus 1. How about the fourth term? When I apply the Hadamard gate, I get what? 1 over square root 2, 0 minus 1 because it's 1. And then the last one, again, doesn't change, right? Okay, now it's going to be a little bit messy. I would rather to continue on this page. I'm going to collect the term. I'm collect it so that I'm going to make the 1 over square root 2 out. Then I have this to keep the normalization. The first one, 0. When the first qubit is 0, right? You span it out. You have 0 times f of 0, right? And then what is the second term? This is 0 times f bar 0, right? And then the third one is f of 1, correct? 0 times f of 1. Right? I'm trying to collect the term. The first qubit is 0. I get f0, negative f0 bar, f1, negative f1 bar. It's very messy here. Maybe I should show you the plus minus method first. But do you agree with this? Then I do the same thing, the whole thing plus 1, right? I still have the one term that I have not tried. This is what? F of 0 minus f of 0 bar, still minus f of 1, and then plus f of 1 bar. Let me check if it's same as my cheat sheet. Is this okay? Because 1 have f0, 1 negative f0 bar, 1 negative f1, 1 negative times negative, so positive f1 bar. I just collect the term. From here, can you draw some conclusion? If it's a balanced function, what does it mean? It means f0 equals to not f1. Because f0 is not equal to f1, then it must equal to the negation of f1. Am I right? When it is balanced, right? When f0 is 1, f1 is 0. Then not 0 is 1, right? So similarly, I have f1 equals to not f0. Let's take a look. If that is the case, f0 equals to not f1. f0 here, do you see that? Equals to not f1. f1 equals to not F0. This term is gone. Only one left. If I do the measurement, I will only measure one, right? Because they got cancelled. Is this okay? Now, let's look at this very long, right? Let's look at this one more time. How many qubits do we have in this lengthy expression? Again, it's 2 qubits. This is the first qubit. This whole thing is the second qubit. Why I have 4 terms? It's just a superposition of 4 qubits, which may be the same also, right? And the whole thing is a superposition of two basis states. One is 0 something, and other is 1 something, right? So if it is balanced, I show you that F0 must be equal to F1 bar. So F0 minus F1 bar, gone. F0 bar equal to F1, cancel, gone. Here, if you try to go through the math, you see that this is non-zero. So you only have the one state left for the MSB. If this is a balanced function, it means that if the function is in this form, B or C, if this is the function I'm testing, when I go through this algorithm, I try to measure the most significant bit. I can only get one. Only get one. And then every time I measure is 1. I measure it 1 time is enough. I get 1, then I know that this is a balanced function. Make sense? If it's a constant function or a non-balance, then it means F0 equals to F1. Right? It also means that F0 bar equals to, what is that if it's constant? F1 bar. Looks like this. Arrow F0 equal to F1, cancel. F0 bar equal to F1 bar, cancel. You are not going to measure 1. You always measure, 0 in the MSB. So this Deutsche algorithm is such that if you measure the most significant bits after this algorithm, you get 1, then you know that this is a balanced function. If you get 0, you know this is a constant function. Yeah, so this is easy, right? Yeah.
So in a nutshell, it's not
Exactly. Yeah. So, this is a very important. I am not good at that, but in computer science, in the optimization problem, this is very interesting. Like the traveling salesman problem, you have heard about the NP hub problem, the optimization. They're very difficult to optimize. Let's say I want to sell, I want to advertise, and that's why some car company, I forgot which one, GM or Ford, right? They are doing quantum computing now as a customer because they want to see what is the best way to distribute their car supplies and also to the dealer. What is the best way to deliver this car to all the city? And each city has different ways. San Francisco has a lot of sale, right? Mercedes may be less, right? Fresno a little bit more. What is the best path to transport all this or to build up the supply chain so you can optimize the logistic? This is super important, and that is optimization problem. Portfolio, you gave your investment manager for, let's say, 1 million. How should he or she invest so that it meets your constraint? You want to have 11% return every year, but you only can afford this risk. There are tons of portfolio, CD, government bond, high risk stock, foreign stock, whatever. they can tons of combination, which is the optimal one. These are the optimization problem. It turns out many optimization problems can be mapped into some fundamental problem, like the coloring problem. Like on the map, how many color do you need to color all the countries so that no adjacent country get the same color? What is the minimum number of color that you can use? And how do you color it? And the same is so-called like satisfiability problem. And this problem, I'm not good at that, but my knowledge is that this will be related to this, because turn out all the difficult problem can be transformed to this very useless problem, like coloring problem. Coloring problem looks like very useless, but they're equivalent to other important problem. You can transform them theoretically. If you can solve this coloring problem, or like this balance or non-balance problem effectively, then you can solve those problems effectively also, because they're equivalent. Yeah.
Well, so I guess if you classical two problems, so I guess that's the question.
Yeah. Because we're only talking about 1 qubit. So as I said, this is a simplified problem or so-called Deutsch-Jozsa problem. The Deutsch-Jozsa problem actually will, instead of mapping 1 qubit as the input, it can have any number of qubit or bits, any number of bits. Your input can be 1 million bits. What if I have 1 million bits? How many combinations I need to calculate? 2 to the power 1 million. And I can do this in one computation to know that whether it's balanced or non-balanced. I only know this. Yeah. Okay, so here, because this is our first algorithm, and I only stop here also, we will go to other algorithm, right? But you understand this, you just go to Wikipedia, read it, you will understand what they're talking about already. It's the same, the theory. Okay, yeah, so that's a very good question. Why this is important? You should talk to the computer science guy. I have limited knowledge, but I understand it's all the difficult problem that is important to your life, including your investment, logistics, whatever, can be mapped to some problem. This is one of them, maybe one of them, or helping them. Yeah. So great. Let me summarize one more time, right? What we just said. We first generate quantum gates. This is for any quantum algorithm. You must have this quantum oracle. It's difficult to explain. We will see this more later. But you just at the first, at now, just take it for granted. But definitely you should know that it must contain what the problem you want to solve. If it doesn't have the problem you want to solve, how can you solve the problem? So this quantum oracle is arranged in some way. It has this information, but it cannot tell you what's the fx, right? Oracle is like, I don't know, the revelation from the God, right? They don't tell you, right? I think this is a good thing. They don't tell you exactly what's going on. They just say, oh, the sky is going to be red, right? Then you need to interpret very vague what is meant by red, right? There's a disaster or actually there will be something great happening, right? That is like this, actually. It's just that I tell you what is y exclusive f of x, but you don't know what is f of x, okay? And you try to extract the information from there. Prepare the state, y plus and minus, not important. It's just because of this algorithm, right? But you appreciate because we want superposition. And after that, we do the quantum parallelism. We calculate them. This is only 2 calculations that we are interested in. But just now you ask, right? What if we have 1 million qubit as input? We do 2 to the power 1 million calculation in one shot. Right? That's why this speed up is really great. Other is talking about exponential, quadratic. We're going to see those algorithms later. This, in principle, actually is just a constant, no matter how big the problem is, one shot. Okay? Of course, all this assume that you can prepare the state, construct the quantum oracle, do the measurement at very short time. These are all the overhead, right? So now we only assume that this UF is going to be very long, maybe 10 years. Great, then in the past I need to wait for 1,000 years for the difficult problem. if it has 1,000 calculation, 100 calculation, now I can get it done in 10 years. That's a big deal also, yeah.
So what you can have millions of people, but the output of the function is only 2 values. Am I reading it correctly, or?
I think it can have many for in the Deutsch-Jozsa algorithm, the generalized one. Yeah, it can have many. So that's why the question is to ask whether this is a constant function, or the output are the same, or it is a balanced function. I forgot exactly, but I think I'm right. If I remember correctly, it is mapping. That is, I have n input qubits. Yeah. Am I right? I think so. Now, why don't we just quickly Google, right? Doesn't hurt to Google. Yeah. I suddenly forgot how many qubits it can have. It doesn't say. Yeah, actually 1 qubit, I'm wrong. Okay.
So the output is
Only one in Deutsch Jozsa. Yeah, so I said it wrong. The input is can be n qubit, n bit, right? Output is 0 or 1. Okay, good question. So I'm wrong. Sorry for that. Forgot. Yeah, but you see that, right? Just look at Wikipedia, right? The last part is actually you just learn, right? 1 qubit case. But here you give you the multiple qubit case. A little bit complicated in math, but actually you should be able to trace already, because last time we played with the Hadamard gate with n qubit. And that's why I spent so much time. Do you remember this one? -1 to the power f of x. This is something we tried last time also, right? When we do talk about that. Okay, so shame, forgot. So, right, this is a general one, right? And then we do the measurement. If 0, then it is constant. If it is 1, it's balanced. How do we construct the circuit? Any idea? How many qubits? 2. And when we do this, we must decide where's the MSB, right? So I decided in this case, I put the MSB on top. Always write this down to be careful. Okay? So MSB should be related to X or Y? X, right? Related to X. So what is the first thing we need to do? How do I do this superposition? Right? We all start with 0, sorry. Yeah. We all start with 0, right? How do I get this state? Plus, tensor plotted minus. Use Hadamard gate. Excellent, right? Obviously, you did the midterm, right? After Hadamard gate, what do you get? Plus. And then I want to get minus. He said that I need to put not identity. I need to put what? The NOT gate. And then I put Hadamard gate, right? Because after NOT gates, I get 1. After this, I get minus, right? And then I say I'm going to put this into the quantum oracle, right? This one, you don't know that, but I just show you here. This one, UF, right? And I'm going to write it in this way. I say, this oracle, I'm going to label it like this. This is a gate, X, Y, X, Y exclusive or F of X. Okay, just a label. It's up to you. Some people label other way. I label in this way. It's just a box, a gate. What do you think? Does the quantum oracle needs to be unitary? And that is why you might already ask why I need both X and Y as input. Isn't that the input is X, output is Y? Why you want to put X and Y as the input? That's because we want to make it unitary. We will discuss later. Yeah, and that is all the complication about this quantum oracle. Very good question, right? So that is why we make this quantum oracle so special. Now, then I apply the Hadamard gate to the top, right? Before I do the measurement, and then I measure. The bottom, useless now. Indeed, it's supposed to be useless. I cannot say that it's supposed to be. I said auxiliary bit, right? I don't need it now. Because if this is 0, then it means this is a constant function or a non-balanced function. If this is 1, then it means this is a balanced function. You can implement this in IBM Q and try it. That is the circuit, right? So we are done with this Deutsche algorithm. Oh, I thought that I want to draw here, so my cheat sheet is a little bit. Why is like this? Yeah, so this one I drew it already. I do want to point out one thing, right? I want to point out one thing. Now, this might help you to understand. Let me draw this better. Might help you to understand better how people came up with these gates. It may be, but may not. But more insights will be better. I just try to write it better. This one. When I say when the measurement, the output is 0 is constant, is equivalent to what? Equivalent to here. If this is plus, then this is constant. If this is minus, this is constant. Because I have gone through, this is balance. Right? Because this is before the Hadamard gate. Right? I want you at least to memorize it, right? When you do a measurement, you use the plus minus basis, you get 0. It's equivalent to applying the Hadamard gate and measure in the plus minus basis. Did I say something wrong? Say again. When you measure plus, you measure in the plus minus basis, it's equivalent to applying Hadamard gate and then measure in the 0, 1 basis. Is that okay? Because if it is plus, after Hadamard gate, it is 0, right? So if I were able to measure in the plus basis, it means that in the spin case, I rotate the magnetic field and measure in the x direction. I try to see what is plus or minus. It's the same as I do a Hadamard gate and then measure in the 0, 1 basis. Right? Because plus equal to Hadamard gate applied to 0. Right? Remember this? Plus equals to Hadamard gate applied to 0. Right? Or you can continue. Remember that what is Hadamard gate times Hadamard gate? Identity gates, right? So they are almost the same, right? Apply Hadamard gate to plus is equal to 0. Right? Yeah. Exactly. If I take away the Hadamard gate, but I need to measure in plus minus basis, then when it is plus, I get constant. When it is minus, I get balance. Yes, exactly. Yeah, that of course, yeah, and more hardware, right? Not hardware, more pulsing time, right? And that's why at the very beginning in the overview, I actually try to simplify it. I only show the plus minus basis, right? With this plus minus basis, you see that it is the same. Try to play with that. But I just want you to look at this, right? Do you agree with me? If it is constant, I will get 0 after Hadamage. It means I will get plus before Hadamage. Now, why I want to point out this? Then what is this oracle? What does this oracle do? Based on this information, can someone summarize in one sentence? How does this oracle help me to know whether it's balanced or constant? Based on here, what will you say? What will you tell someone? Not even so long, the sentence. What does it do? Maybe you don't know what I try to say. I try to fish for. What I'm trying to say, this oracle, the input to x is plus, right? It keep the output. It keep the output as plus if it is a constant function. It do a negation so that it is minus if it is a balanced function. Now, if you're the inventor of the algorithm, maybe you will start with this. Can I come up with algorithm so I have a state come in? If it is balanced, I keep this state. If it is not balanced, I invert the state. You might start with, wow, what if I have input is 1? If it is constant, I keep 1. If it is not constant, I make it 0. Right? You can have this idea. Then you start to work out, what can I do? Try different circuit. Maybe you cannot get it done. Finally, why don't I try in the plus minus space? You see what I'm trying to say? This type of insight, right? I don't have, but I guess that is what those people have, right? And that's they come up with the algorithm. And start from here, then they start to thinking, how do I really implement it? And then plus, we know that we need superposition. Plus, we know the oracle need to have f of x. I think this will just limit you to have this final circuit. Maybe you have other variation, right? Okay, so let me write this down. The oracle, right? This is like not, how do you say? I have this after you see this circuit, right? Not a priori, right? It's not prior, right? Keep plus x if f of x is constant. Right? You invented a machine, which is almost not answering the question, right? If it is balanced, then it is balanced. If it is constant, then it is constant. You just change a little bit. If it is balanced, don't change the state. If it is constant, then change the state. Then you keep thinking how to implement. That's what I think, right? I mean, the first time I studied this, I did not realize this is after many more study, then I realized that, oh, actually I can see the oracle in this way. That is the function of the oracle. And then maybe you start make up the equation, right? Play with that. It's just like I give you a differential equation, you want to solve it. You have some systematic way, but very often you try to make up a function that satisfies the equation, right? Maybe this is cosine e to the power something, but I need d it, then I have the I phi in front. How can I make up this? Maybe then I have a negative sign, and then whatever. Eventually come up with the solution, right? That is the insight, right? Of course, you have some systematic way, but I think if you want to invent an algorithm, you need to do this. That's what I want to share with you. Okay, any questions?
Is it not possible to take the x out and then put there, just initialize the LSB to 1? I mean, there's nothing wrong or impossible about quantum computers initializing to 1.
Yeah, you can. The problem is that you go through the math, it will not work because we need to have some cancellation. Yeah. Why don't you try that at your leisure time, right? Do not do this. If I just put 1, I keep this 1, can I come with something?
The X gate or LSB, the one
You want to what? Remove this? Oh, you mean initialize this to 1? No, but as we said, right, in all quantum computer, we prefer to initial everything to 0 at the beginning. You can say you initialize this to 1, yeah, but to initialize it, actually apply an X gate. Remember what is X gate? It's just a pulse, right? So you initialize it to 1, isn't that you need to apply a pulse to it? You already apply an X gate, but you just try to hide it.
At the end of the day, these machines are just one, right? So I don't see why that it's possible.
You can, but how do you initialize to 1? But tunnel current is not a quantum. Yeah, you need to be spin up, spin down, high energy, low energy state, right? You can, but how do you get there? You need to apply a pulse, some energy to bring it from ground state to the excited state, right? And that process is already a gate. Right? If you're talking about spin, the reason why we start with initial at 0, because how you can ensure all the quantum qubits are at the 0 state is very easy. Cool it down and let it thermalize decay, or will go to the ground state. That's why we want to start with ground. And how do you make sure that qubit is at 1? You need to let it go to ground and then apply an excitation pulse, bring it to the higher level. Otherwise, you have no idea whether that is at 1 or 0, right? Give you any arbitrary system at the beginning. Right? I give you a bunch of electron or spin. Do you know whether they're at 0 or 1? You don't know. Then it means you need to do measurement. And once you do measurement, then it's complicated, right? How do you know that I give you 10 electrons? How do you know they are all spinning up or spinning down? Align with the magnetic field, but then it can be a high energy pointing up or pointing down, right, at the beginning. You only wait for a long time, all those at the high energy would decay to the other direction. And then now you say, I wait for 1 second already, I think all my system is at ground state. And then now you do whatever you want. You say you want to initialize at 1, then again you need to apply a high pulse to bring it to 1. Which is equivalent to applying a gate. Remember, again, all these gates is not a physical gate, right? These are just a pi pulse. Right? We talked about this in E274, quantum computing architecture, right? Yeah, that's a very good question, right? And that's why we all initialize to 0. And in reality, you go to IBM Q, they all initialize to 0 because they don't want to. It's the same, but I mean, it's easy for their algorithm. Everything is 0, and then you decide what you want to do. Apply the pi pulse yourself. Yeah, good. So this is the algorithm in a nicer drawing, but now be careful. This is MSB, this is LSB. This is what we had before, right? I drew on the slide. This top one is swap MSB at the bottom, LSB at the top. That is the circuit you will draw in IBM Q. And this is the circuit in IBM Q, right? You see that first I have a NOT gate because the top is LSB, remember, okay? This is Q0, so this is Y, this is X. Right? So I have the NOT gate for the MSB, right? And then both of them go through Hadamard gate. Now, this one I won't explain now because you need to do this in your project. Not project or assignment, I forgot, right? This one is the oracle. Now, I don't have a physics system with me, right? I don't have the nature of God to give me the oracle. I am the one who created the oracle. So here I create a constant oracle. It's just an identity gate, right? I won't explain here. It will be in my book. You can take a look. But most importantly, you need to do it in the project, the assignment, right? So you need to create 4 oracle corresponding to the 4 different types of function. But anyway, here when I measure, I always get 0, the LSB. which means this is a constant function. When I put in the real computer, I get some noise because of the imperfection. Okay, yeah. Is it a Deutsche algorithm, right? Yeah, you need to implement the 4 quantum oracle. Now, this is a little bit confusing. I don't want to be as specific now. I want to think about that. Because again, some of you think the question is difficult to understand. But if you understand the question, it means you really understand the